How many of you are familiar with Wordle? Uh, it's an like, do you play Wordle? Uh, I see one or two hands. Any more? Okay. Uh, I think snake and ladder is more common, right? Okay. So,
This is the PowerPoint.
what's the common
This is the
thread
PowerPoint.
between these two? Like those people who have played both the games, any idea?
Can you do the PowerPoint?
Okay. Uh, so Professor Sinha is here. He is going to talk about that, like how we can connect these two and how it has been modeled. Professor Sinha is in MSc for last 22 years. He has been teaching physics as well as computational biology.
Just open the link.
And he works in quite interesting problems like
Can you just go down?
why there are certain
down,
sort of,
just see the
like
link is
traffic
opening.
signal problem in
Yeah.
Chennai
Can you just
and
open
why certain kind of video gets viral. So now today we are going to learn Wordle or Snake and Ladder, this kind of board games, how they are connected and how it can be answered.
But hopefully, since I'm going to talk about games, you'll hold on to your hunger for a bit more time. So, as Nandini asked, hopefully some of you have played Snakes and Ladders. So, how many of you have played Snakes and Ladders? Okay. Actually, there are quite a few who haven't played it. Okay. So, just to tell you, so this is played on a board like this. Okay. So, basically you have this boxes marked 1 to 100. Okay. You roll a die, and as you know, it has numbers marked 1 to 6. And so if you get a 4, for example, you go 1, 2, 3, 4. Okay. Then if you're playing with someone, that someone rolls a die, and let's say he got 3, 1, 2, 3, he immediately goes to 21, whereas you are left at 4. Okay. And so this goes on, but occasionally, let's say your opponent comes to 62, and then suddenly you go down to 22. Whereas let's say you have already gone to 43, and then if you're lucky, you can go to 58 and you can move on to 77. Okay. Sounds complicated? Okay. I will just show you. There's actually a site on the net, toytheater.com, where you can actually play Snakes and Ladders online. So let's see whether this works. So I'll play with the computer. Okay. So this is a two-player game. So let me choose white. Okay. So basically, it gives you a simple instruction that the goal is you have to reach 100. Whoever reaches 100 first wins, and you roll a die. If whatever comes up, you go that many squares. If there's a ladder, you can go fast. If there's a snake, you basically go down. All right. Very simple instruction. All right. So there's my die. So let me roll my die. So I get 1. So immediately I move over here, and my opponent gets to here because it played 6 once, and so it got an extra turn, and so it got, I think, 6 again, whatever. I think it got 6, 1, 6, 6, 6, 1, so it has now moved to 12. Okay, so now I have to roll my die again. So I roll my die. So I move again just a little bit here, and my opponent has moved here. Okay. Roll my die again. So I get a 5. Okay, and my opponent has 2, and it falls straight in the mouth of a snake and goes back to 6. Okay. So you get the idea of the game, right? So I get a 1, my opponent gets 4, then I move 1 again, my opponent gets 2, roll it again. Again another ladder. I'm really lucky. Okay, so now I'm here, right? I am at 67. Okay, whereas my opponent is still stuck at 13. Okay, so let's see if my roll of luck continues. So you think the game will get over very soon? Well, guess what? Now I'm at 91. I've been really lucky. I've hit 3 ladders, right? So, no, my run of luck ended, right? Okay. So now my opponent is, guess where? My opponent is actually in front of me. It's at 84. How did that happen? Just 2 turns back, my opponent was here and I was there, right? So this is the charm of snakes and ladders, right? Luck completely decides who gets to win. And you think the game will get over soon, guess again. The game can continue for a long time because as soon as you reach somewhere over here, you fall in the mouth of a snake and you keep going down. If you're really unlucky, you can actually fall in 87, go back all the way to 24, right? So one of the questions we can ask is, how long will this game go on if you were playing with yourself, for example? Okay, I'll come to that in a moment. Just to point out that to those of you who think that this is a new game, think again. It's actually developed in medieval India. So we have evidence that in 13th century, it was definitely played, and some sources indicate that it was actually known to 10th century Indians. Okay, and of course this game had a completely different name. It was not called Snakes and Ladders. It was known to some as Mokshapatam, and later when the Jains used this game, they call it Gan Chopper or Game of Wisdom. Okay, and as like most Indian games, like chess was developed in India as a way of teaching strategy, right? So games were always developed in India with a particular purpose in mind. So the purpose of Mokshapatan was to show the role of destiny in our life. And each of the squares essentially corresponded to the state of our spiritual health. Okay, so if you were leading a path of holiness, so if you were like good, then you could move up quickly along these ladders. So the ladders represented generosity, faith, humility. But if you were leading a life of vice, then you would fall in the mouth of a snake and go down. So the snakes represent vices such as lust, anger, murder, theft. And so the morality lesson here is that you have to reach moksha, okay, which is here. So notice that it was not actually in square 100. It's somewhere, in the middle of the final row, and there's a reason for that. So let's say you manage to get everything correct, and you reach over here, then you have reached moksha. You will not be born again. But suppose you don't get it right, you can actually cross this square, and then guess what? You start in the beginning. That means you are reborn. Okay, so this entire cycle of birth, death, rebirth, and so on was taught by this game of Mokshapatan. And typically the number of ladders were much less than the number of snakes. That's because following the path of good is always more difficult than following the path of evil. Okay, and that turns out to be actually quite critical. The number of ladders to number of snakes, and the total number of snakes and ladders actually decides how long you will go on playing the game till you reach moksha or till you reach the finish, 100. And this actually brings us, sorry, I think somehow this, oh sorry, it was just a delay. This brings us to these interesting questions, okay. So suppose you're playing this game on a board. So the typical board has 10 by 10 squares, so 100 squares, and there are a total of 19 snakes and ladders. Okay. So how long do you think on average you will need, how many turns you will need to finish the game? Any guesses? How many times would you need to roll the die before you will reach 100? Any guess? Anyone want to guess? Well, one simple way of saying that, I have a die which basically rolls between 1 and 6. So on average, I'll probably roll 3. And let's just say that, I would need at least 33 turns. On average, I would need 33 turns to get to 99. So you can, make some kind of argument like that, that if there were no snakes, no ladders, then maybe 33 moves. But now there are snakes and ladders. Okay, so I could finish the game early, I could finish the game much later because I'm keep going sliding down with the snakes. But if I turn lucky, strike lucky, I can go up the ladders. Okay, so any guesses? How many turns do you think you will need? 20 to 25. Okay, good guess. Anyone else? So let me just write down somewhere. Okay, so let me ask, how many people think it will go down from 1 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70, and maybe greater than 70. Okay? Okay, so I got so far one entry. Anyone else? 30 to 40. Good. Anyone else? Yeah. 30 to 40, okay. 40 to 50. 10 to 20, okay. Anyone else? 50 to 60. Okay, anyone else? Just remember what you said, okay, because later we'll see the answer. Anyone else? 40 to 50, okay. 30 to 40. Actually, we will see, there's something called wisdom of crowds. Sometimes you just average out what people have said and you get the right answer. So let's see if we will have that. More. Sorry? 30 to 40. Greater than 70 or 60 to 70? Which one? 70 plus. What else? Let's see. Come on, quick. 20 to 30. Okay. See, there's no marking, right? You won't miss lunch if you answer incorrectly. You still get lunch. Sorry, 30 to 40. Okay. Anyone else? 30 to 40, 1 to 10. Okay. 40 to 50. Anyone else? Greater than 70. Okay. Last chance. 10 to 20. Okay. 22? Someone said something. Sorry? 20 to 30. Okay. I hope you are not giving two answers. Okay. So fair enough. We got a good representation. So if you go by wisdom of crowds, this would say that, 30 to 40. Because this is where the peak of our distribution lies. Let's see whether that will be correct or not. But before that, two more questions we can ask. So suppose now you are playing with the computer, okay, or you're playing with another person. So how long would a two-player game last? Now you might say, hold on a second, isn't it the same as what you asked before? So when I'm just playing by myself, no, because now I'm asking that any of the players reaching 100 would finish the game, right? So now you're asking two players are playing, how long would it take for any one of them to reach 100? Which is a slightly different question from asking, how long would it take on average for one person to reach the end? Okay, so it's a subtle difference, right? Another question related to it is, so in any two-player game, someone will have to finish first. Sorry, begin first. So does that person have a higher probability of reaching the finish before the person who starts second? Is there an advantage of finishing first? No. Okay. Let's just check the answers. Okay. I won't tell you the reason why I'm telling the answers now, because that is what the talk is about. Okay. I think there's a delay. Okay. So first, Actually, it turns out wisdom of the crowds is totally right in this case. Okay. It takes about 39 rolls of the die to finish the game if you're playing by yourself. Surprisingly, if there are two players playing, it takes slightly longer. It takes about 48 moves. Okay, so you would think that if two players are playing, and the question is, at least one of the players have to reach the finish line. You might think, okay, it will take probably shorter than 39, fewer than 39, but no, it actually takes about 48 moves to finish the game. And lastly, the first player actually has a slight, extremely small 51% chance of winning the game as opposed to the second player, which has 49% of winning the game. Very small advantage, but if you are playing the game for money and if you are playing it again and again, this is going to be a big, difference. All right. So, this calculations, of course, assumes something that, throwing a 6 does not allow you to, do an additional roll, and that the player must roll the exact number to reach the square 100. So, if you're at 99 and if you roll 3, then you have to wait until the other player plays before you can again roll. So, until you get a 1, you won't be able to finish the game. So, then you can show that the probability of finishing the game as a function of the number of times you roll the die goes something like this. So, the more and more turns go, closer and closer it comes to the probability of 1. That means you are certain to finish the game, but it's, very slowly converging. All right. Now, how do you figure this all out? So, okay, you might say I can play this game again and again and again and note down the numbers. How many times did it take me this time to finish the game? How many times did it take me to this time to finish the game? So you can play the game, let's say, thousands of times. You can, from there turn out the average number of turns you require to finish the game and you can work it out. But if I want to have a very general theory, then I can answer the questions even if I change the number of snakes or I change the number of ladders or I introduce additional rules like in, the original GAN chopper in which you don't attain moksha at 100, you actually attain moksha at 95, and if you cross 95, you actually start the game all over again. Okay, so then I can ask how many times, how many turns will you have to go through to go, finish the game. So obviously that will be much, much bigger than, 39. So if you introduce these kinds of changes, obviously every time you change each rule or each, let's say, number of ladders, you will have to again play the game thousands of times before you can get the answer. So we need some kind of a mathematical framework to answer these questions. And so we move on to a bit of maths. So it turns out that if you have a game where from any square, the odds of moving to any other squares are completely fixed. So from any square, let's say you start from beginning 1. So the probability of moving from 1 to 2 is what? If you have a 6-headed die, what is the probability of going from 1 to 2? 1 by 6, correct. 1 to 3, 1 by 6, 1 to 4, 1 by 6, 1 to 5, 1 by 6, 1 to 6, 1 by 6, 1 to 7, 1 by 6, 1 to 8? 0, correct, right? And so, we know exactly, so 1 to 8, 1 to 9, 1 to 10, all of these are zeros, right? So, now given this, you can actually map any type of such board game to a mathematical form known as a Markov chain, okay? So, what is a Markov chain? So, this is something that was invented more than 100 years ago by this Russian mathematician, Andrei Markov. And his idea was that you can treat how something changes, anything, a game or the weather or life, anything that changes over time as something where events happen as a sequence of chance events. So something random happens, and so you undergo a certain change, then something else happens, you undergo another change and so on. And so if you take this perspective that everything is just happening because of pure chance, then you can model that process as a system where you go from one state to another simply through random chance where the probabilities of moving from any state to any other state are given. So Markov chain essentially is a mathematical form which tells you how, if you are given a set of states, so in this particular case it's basically the squares in the game board numbered from 1 to 100, and the transitions, how you go from one to the other. So what are the conditions? The, the system, in this particular case the game, has to belong to any one of a set of states at a given time. So that means you have to be on any one of these squares numbered 1 to 100 at any given time. You have a evolution, that is you change in time as a result of going from one state to the other. So you roll a die, and for example from 1 you can move from 2, 3, 4, 5, 6, 7, but not to any of the others. Okay? Then the future depends on the present. So where you will be one turn later depends on what number comes up when you roll the die. So depending upon whether the number 4 comes up or 6 comes up, you will be moving to 5 or 7 and so on. And the future does not depend on the past. So suppose you're here on 47, where you will end up, so you'll probably end up in 48, 49, 50, 51, 52 or 53. So it only depends upon what your die, when you roll it, turns up. It will not depend on how you came to this 47. It does not depend on whether you came at 47 from 42 or 44 or 46. Okay. So these are the only, so this means that it does not depend upon what happened in your past. Your future only depends upon what you are at present. What happened in the past? Completely pointless. Okay. So this is what defines a Markov chain. So what's the difference from, let's say, a coin toss kind of random process? So remember, in a coin toss, it does not even depend upon what side the coin was flipped currently. So I hold the coin in my hand, let's say it's either head or tail. When I flip it, it does not depend upon whether I flipped it with my head or a tail on the top, right? So it is completely without memory, but this is contrasted with this Markov chain where you have limited memory. So for example, you want to know what is tomorrow's weather. So tomorrow's weather could be sunny, rainy, windy, stormy. In Chennai, of course, we won't have snowy, but we can have cloudy. So the weather tomorrow depends a bit on the weather today. So if it is rainy today, chances are that it will probably be rainy tomorrow. If it's sunny today, chances are that it will probably be sunny tomorrow, and so on. But it may not depend upon what it was 2 weeks earlier. Okay, so 2 weeks it was very sunny, but yesterday it was rainy, so very likely that tomorrow may be rainy too. So there is some dependence on what happened in the present which decides what happens in the immediate future. So this is what differentiates Markov chains from simple coin toss type of randomness. So let's take another board of game to demonstrate this. Let's take Monopoly. Okay, so Monopoly originally was not even designed by Milton Bradley, the company which sells it. It was actually designed by this lady, Lizzie Magie, who was a socialist, who actually had designed this game to show how bad Monopoly is. But capitalism is so canny that they managed to take a game which was supposed to criticize it and turn it into a money-making enterprise. Okay. So what this game does is that you start from here, then you roll 2 die, and then this roll of this 2 die decides how far you will move. Okay. So what are the possibilities? You can roll 1 and 1 in the 2 die, so you move 2 steps, or you can roll 1 with the first die, 2 with the second die, or 2 with the first die and 1 with the second die. In either case, you will move 3 squares. Then you can roll 1 with the first die, 3 with the second die, or 2 and 2 with the first and the second die, or 3 with the first die and 1 with the second die. In any of these 3 cases, you will move 4 and so on. And all the way up to you can, have 6 and 6 in both die, in which case you will move 12. So this actually helps us to work out what is the probabilities of going from the go to any of these other squares. So from looking at how many ways you can go from go to 2 or go to 3 or go to 4 or go to 12, you can work out the probabilities. And this tells you that because there are 40 squares, the system has at least 40 states. Because you can have 11 possible ways in jumping from any square to any other square, there can be at least 40 cross 11 transitions between states, because why 11 and why not 12? You have 2 die, right? Yeah. Very good. Excellent. Excellent. Yeah. Because you can throw one with one die and one with another die. So you start with 2. Okay. So you can throw 2. So you can get 2, 3, 4, 5, 6 up to 12, which actually has 11 moves in all. And where you end up depends upon where you are on the board at present, and it does not depend on how you got to that square. And so therefore, this defines a Markov chain. Now, analyzing monopoly, because it has 40 states, is quite complicated, and since we don't have actually that much time to work it out, let me work with another very simple example with just 3 states. So this is a simple model of weather. It could be sunny, it could be cloudy, it could be rainy. Okay. Now, if it is sunny, then there's a 60% chance that tomorrow would be sunny. Okay. But there's a 30% chance that tomorrow will be cloudy and a 10% chance that tomorrow would be rainy. Similarly, if today is cloudy, there's a 30% chance that tomorrow will be cloudy, 20% chance that tomorrow will be sunny, and a 50% chance that tomorrow would be rainy. And if it is raining, there's a 50% chance that it will rain tomorrow, 40% chance that it will be sunny, and 10% chance that it will be cloudy. So we have given all these numbers. Now, given these numbers, we can actually create a row of numbers. So this is sometimes known as a matrix, which tells me that given the weather today, what is the probability that the weather tomorrow would be sunny, cloudy, or rainy? So for example, if it is sunny, tomorrow would be sunny, the probability is 60% or 0.6. If it is rainy, tomorrow would be rainy with a probability of 50% and so on. Right? So this is basically just putting into a matrix what we already saw there. Okay? But what's the advantage? So now given this, I can actually be able to tell how the probability that it will rain day after tomorrow if it is cloudy today. How do I do that? I take the row for the cloudy day and what are the different probabilities of that tomorrow would be rainy, sunny, rainy, cloudy, and multiply it with the column which corresponds to the fact that day after tomorrow would be a rainy day, which is 0.1, 0.5, 0.5, given that tomorrow is sunny, tomorrow is cloudy, and tomorrow is rainy. So now I multiply this and I get the probability that if it is cloudy today, day after tomorrow would be rainy is 42%. So you see that given just the probabilities that what the weather will be like tomorrow, I can work out what the weather will be like 2 days later. And similarly, I can work out what will it be like 3 days later, what will be like 4 days later, 5 days later, 7 days later, and so on. And you will find that eventually these numbers become identical. So that means it's no longer depend upon what the weather was like today. So if you go far enough in time, you will find this probabilities no longer depend upon the weather today, which means that very far in time, the information that you have today doesn't matter. So you can't predict what the weather would be like several weeks later. Now you might think, okay, weather, fine, important, but you can actually apply it in all kinds of different things. So for example, doing poetry. And in fact, Markov's original paper actually applied this on poetry. And so he said that, look, can you actually generate poetry of Pushkin by using Markov process? So what you do, you take Pushkin, a famous Russian poet's poem, Eugene Onegin. You take the statistics of this letter, so how many times each letter appears. So you'll find out that the vowels appear 7,788 times, consonant appears 12,000 times, 2 vowels occur one after the other 1,300 times, vowel and consonant appear 6,400 times. And knowing all these probabilities, you actually use this matrices to generate letters and words. Guess what? If you just have first order statistics, so if you just predict the next letter given the initial letter, it looks like this in English. Okay, so it looks complete like something from Lewis Carroll, right? But when you go to third order, that is you use what happened in the past 3 letters, it starts to look, vaguely surreal, right? At once and no fall, make a stick to us, in face, very, very, William, the author of James Joyce, very James Joyce-ish. If you look at fifth order, it starts looking vaguely, realistic. Meanwhile, with jealousy bench, and so it was his time, but she tricked, let message be visits. And at seventh order, it really genuinely reads like poetry. My sorrow her breast over the dumb torment of a veil, with her poor head is stooping, but now Aurora's crimson finger, your christening glow. Farewell, Ebony loved one, honored fate by calmly not yet seeking. So, it beats ChatGPT, right? It actually genuinely reads like poetry, and this is just random chance. Okay, and this is something that was rediscovered by Shannon. In the last talk, the speaker talked about Shannon. So Shannon, as you can see, was a real fun guy. So this is him juggling with balls while riding a unicycle. And Shannon actually applied this on English, and he showed that actually you can, generate random text which read vaguely like actually genuine English. And guess what? He actually used to predict an English text if spaces are missing. So suppose you are given this original text, the room was not very light, a small oblong. And suppose I now take out lots of these letters. Now, it looks kind of difficult, but if I take out only a few, for example, this one, here you might still be able to figure out what the correct letters are, simply because you know that between P and L it's very likely a vowel, and it could be either a pa or a pa or a po, but if it's a s, very likely it will be Polish, and so on. And this is precisely what is used by autocorrect and predictive text. So when you use a WhatsApp, and WhatsApp automatically corrects your text, sometimes much to your irritation, what it's doing is exactly using this Markov chain. By looking at a huge horde of word statistics, letter statistics, and so on, if you type the first few letters, it's trying to quickly complete the rest of your letter by doing this Markov chain calculation. So you can start with something like this, I, and immediately, by going through all the possible ways in which English sentences can be formed, you could say a I am, or a I do, okay, or I love, and then if you take this path, I am, so that it could be I am only, or I am tired, or I am so, and then let's say you take this path, so you could say I am so, or I am so tired, or I am so happy, and so on. So you see that each of this could be generated simply by looking at the probabilities which you have looked up from reading or calculating the statistics of lots of English texts. And in fact, this is precisely what allows you to solve this problem known as Wordle. So those of you who have played Wordle, of course, know what it's about. Essentially, you have to guess a 5-letter word in 6 attempts. Now that seems impossible, right? How can you guess a 5-letter word, which could be anything, crown, for example, just having 6 chances? Well, you're given some help. So, for example, suppose you guessed crown. So then it says, well, C is actually appearing in the word, but it's in the wrong place. So you know that the word has C, but it's not here. So next you try paste. Okay, so it says that, okay, A, C, E are all in the word, but are not in these places. And then you try, okay, A, C are there, so let me try acute. So it tells you A, C, T, E are all there, but not in the right places. So then you say, okay, since A, C, T, E are there, what words uses that? So you try enact. So it says, okay, A and C are now in the correct places, and E and T also appears, but they are not in the right places. So, okay, so you say, okay, A and C should be there. So let's try trace. Okay, so it says TAC is there, E is in the wrong place. So since E is in the wrong place, as this is the only place left, T and E should be here. So it's TEAC. So what should be here? So you say, okay, if it's TEAC, the only possibility is teach. Okay, and so you can attempt, and you can often solve Wordle in 6 attempts, but if there were no such correlations, you would have required how many? 10 million guesses to actually solve the problem. Okay, so this is actually all the possibilities that are there if there are no correlations. Okay? So let me finish by saying that Markov process is of course a model of the world, and as they say, all models are wrong, but some are useful. And so essentially, as Frankel said, the more complicated the system, the more simplified must its theoretical description be. So a good theory of complicated systems should represent only a good caricature of these systems, exaggerating the properties that are most difficult and purposely ignoring all the remaining inessential properties. So the benefit of doing Markov modeling has been that not that it accurately describes a real phenomena, because often you see that language has lots of previous dependencies, not just immediately the word immediately before it, but by stripping down to a single mechanism, it helps us understand the underlying idea at a great depth, and it can help us to extend it to different problems. Okay? And let me finish by showing the one of my favorite comics artists, Alan Moore's, that the end may not always be the end, So that's why we come back to the concept of rebirth in Snakes and Ladders. Thank you.